What I'm going to talk about now is another important application of these sorts of ideas, but we just don't have a lot of time to go into it in too much depth, so I'll just kind of hit the highlights. Let's say you have a prism, and unfortunately I don't have a prism here that's shaped quite the way I want it, so I'll just have to draw it out. A prism is just a piece of glass or some other high-index material that's shaped like a triangle, right? And if you shine a beam of light through a prism, well, actually two things will happen. One is you'll actually get what's called diffraction, meaning that the colors will separate, or white light will separate into its constituent colors, right? We're not going to focus on that too much. We're just going to focus on, let's say you have a monochromatic beam of light. We're not going to worry about the color separation. And we're just going to look at the refraction through this prism, okay? So let's say I have a beam of light traveling in this direction. And it hits this surface. And so I have, this is air out here. So this is low index, and we have glass, high index here. Well, it hits this surface, but we have to draw the normal to the surface, right? So there's the normal to that particular surface. So if it goes from air to glass, it's going to be bent toward or away from the normal. Toward the normal, okay? So it's not going to go straight through. I have to draw the new light ray kind of like that, okay? So this angle between here and here is smaller than that angle. And that light ray will continue through until it hits the next surface. And now we have a surface at a different angle. And that is the normal there. And so we have that angle between the normal and the incoming light ray. But now it's going from the glass into the air, so now it's going to be bent away from the normal, right? So I should draw this angle bigger. And it's a little bit hard to draw, but you can see that angle, I'm trying to draw this angle being bigger than this one. It's bent away from that normal. And so it happily proceeds along in that direction, right? So we have a way to actually change the direction of the light beam as it goes through from one end to the other of this prism. What if I have another prism? Let's say I have another prism here. I'm going to draw it in the opposite orientation. And I have another light ray that happens to be parallel to this one coming in. And it hits this interface, and again it's going to be bent towards the normal. So I draw this angle smaller. And it hits this interface, and it's going from glass to air, so again it's going to be bent away from the normal. And so we're going to have something that looks like that. And now I have two light rays. Initially they were parallel to each other, coming maybe from some distant source very far away, coming in parallel lines. And after they travel through these two prisms, they're bent toward each other and will actually converge and meet at some point. What have I just made? What is this called? It's a lens. It's probably the simplest lens you can think of. It's basically just two prisms or two angled pieces of high index material, angled in such a way so that on the top half, light rays are going to be bent downward, and the bottom half, parallel light rays will be bent upward, and they'll meet somewhere in the middle. Okay. So I could, instead of having this ugly shaped prism, I can do something like this. Have a piece of glass maybe shaped like this, where it basically does the same thing. If you look at a tangent line to this curve, it's bent in that above the center line here, it's bent, it's tangent in such a way that it's going to cause light rays to bend downward. Down here, it's angled the other direction, just like this prism, and parallel light rays will be bent upward. Okay, so this is called a converging lens, because it makes light rays, parallel light rays, converge to some point. What if I wanted to make a diverging lens out of these two prisms? What do I do? Yeah, just flip them, right? Make it, yeah, exactly. Make it look like an hourglass. So that if you had something like that, you have a light ray coming in, bent toward the normal inside the prism, bent away from this normal as it exits the prism, and that light ray goes off and diverges away from a parallel light ray down here, which is bent toward the normal, and then again bent away from the normal. And so this is a simple example if you wanted to do something maybe look like this, where it looks concave, at least on one side. Could look actually, this is another example of a diverging lens could be something like this. It doesn't have to be concave on both sides, as long as it's thinner in the middle and thicker on the edges, whereas a converging lens is thicker in the middle and thinner on the edges. So this is a diverging lens. And we can show that. Okay, so we have parallel light rays, and if I place a converging lens there, right, we have it's thicker in the middle, thinner at the edges, and it's all the light rays that are coming in initially parallel to each other are being bent toward a point. And if I have a lens that looks maybe like this, that's not terribly dramatic, but I think you can kind of see how they're bent away from each other. Let's see if I can find a better one. What if we have something like this? This is probably not quite as good. Ooh, that's a mirror. Never mind. That's not a lens. That's a mirror. Unfortunately, we don't have time to go into mirrors. That's too bad, but that's a converging mirror. Do we have a better diverging lens? Maybe this one. Unfortunately, doesn't cover the whole span here, but a lot of weird stuff going on there, huh? Looks like we got some total internal reflection, and what if we do that? Well, it's mostly divergent. All right. But you get kind of the idea, okay? Let's go back to a converging lens. Parallel light beams come in and are converging to a point that's called what? The focal point. Yeah, this is the focal point. And so the definition of this thing called the focal point is if you have a converging lens so parallel light beams converge to the focal point. And the distance from focal point to the center of the lens is called the focal length. I want to show a little demo here, a little virtual demo. This comes from the University of Colorado's website. They have a collection of very good sort of physics demonstration software. And I'll just write the URL on the board because you might want to actually play around with it yourself. It's free downloads. URL is phet.colorado.edu. And they have demos in all sorts of subjects, but I kind of like this one on lenses. Here's an object, okay, and what we're drawing are light rays. These are called we're drawing, first of all, we know that light from some source is propagating in all directions, okay, so here's just a picture that shows many different light rays. But we're going to pick only rays that are going through the lens because those are the ones that we're interested in. So if I can show these ones as the light rays that go through the lens. Now I can't make this object appear infinitely far away, but you can kind of look at this. If I place these little X's here are the focal points. And again, the idea is that you can either have light rays me kill the lights because it's hard to see. Either you have light rays that are parallel to each other coming in from this direction, are focused to a point, but in this particular case we have the opposite situation. This is the source. If the source is at the focal point, then any light rays that emerge will end up parallel to each other on the other side. Okay, so the focal point is parallel rays get focused to that point. When the rays are not parallel, or when the source isn't at the focal point, then the rays may converge at some different point, but where they converge is where an image actually forms. Okay, so this is our source, the thing I'm actually moving around. And if you look at the pencil tip, okay, we can think of one ray going through the edge here that gets bent down, and it forms at this point. One ray that's going through the center, and ones through the center don't get refracted, and it meets that same point, and the one that goes through the edge here meets that point. Geometrically, what we often draw is what are called principal rays, and the principal rays, now this is a little weird because it looks like, well, this ray can't possibly get refracted because it's not going through the lens. And that's true, but we're kind of using it just as a geometric guide. Any ray that is parallel to the center axis, and let me bring it down here just to show. Any light ray that's parallel to the center axis of the lens, when it goes through the lens, it'll get bent in such a way that it passes through the focal point. Okay, so one possible ray is one that's parallel to the axis. It ends up going through the focal point and continues on. Another possible ray is one that goes straight through the center of the lens. That one is not refracted at all, okay, and that continues on. And then another one goes through the focal point on this side. Any light ray that passes through the focal point on this side will be refracted in such a way that it ends up parallel to the center line on the other side. And so we can use those rays as a way to figure out where they're going to converge. Where they're going to converge is where an image is going to form. And that means if we actually placed a screen there, and I don't know if I can do it here. Let me do it. So here's a screen that I can move around. That means if I actually placed, so here the image is now changed to like a lamp. I place a screen right at the point where the image is, and I'm going to see a bright spot. Some light actually does reach that point, and I can project it onto a screen. Okay, so what we call a real image forms, and a real image is one that you can actually project onto a screen. What do you notice about the image compared to the original object? It's inverted. Okay, so why does that happen? Yeah. Okay. So this point down here is ending up below the axis, right? So we would think that any point below the axis would end up above, and you can show that by just drawing a second point. And let's imagine just the bottom. So it's kind of like having the top of the pencil has a little LED on it. Maybe the bottom of the pencil has a little LED on it. We can track the light rays due to both of them. Same rules apply, though. I can draw a beam of light from the bottom of the pencil that goes parallel to the axis. That one will end up through the focal point on the other side. I can draw one through the center of the lens. That one ends up going through unrefracted. And I can draw one that goes through the focal point on this side, and that one ends up parallel to the axis. If I do that, we see that you really do have converging light rays from the bottom here that end up above the converging light rays from the top of the pencil. So the image is flipped, and this is what's true about any real image, at least a real image formed by a lens, is that the image is going to be inverted on the opposite side of the lens. Okay. Now, and that's going to be true for any image or any object that I have that is farther away than the focal length. And I can move them back and forth, and you can see how, depending on where this is, the image might actually be larger than the object, or the image might be smaller. But I will form a real image, or the light rays will converge on the other side. What if I move this closer than the focal length? It becomes a little bit trickier now to see. Go back to this version again. What's happening to the light rays now if the source is closer to the focal length? Are they converging? They're diverging, aren't they? They're diverging. What would we see if we looked through that lens? Magnification, right? Because what would happen? Let's put the pencil like this again. The image would get larger. So if I'm on this side, what it looks like to me is like these light rays are emerging not from this point, but they look like they're emerging from some point farther back. Okay, if I trace these light rays back along a straight line, they're going to converge, or at least to me they appear like they're converging from some different distance and a larger height off the axis. And so I can't form, now these light rays aren't really coming from this point. I can't form, if I put a screen there, I won't actually see anything projected onto a screen. But it looks to me like they are coming from that point. That's called not a real image, but anybody know? Virtual image. Yeah, this is called a virtual image. So a virtual image for a converging lens like this is, the virtual image is actually on the same side as the object, but it is larger, it's magnified, and it's up right side up. It's not inverted. So we see it, it's virtual because it appears to us to be coming from this point, but it's not really. Okay, the light rays are really coming from this point and just being bent in such a way that they diverge. Okay, that's the basic idea, at least for converging lenses. Okay, and so you get convergence if your object is farther away than the focal length, divergence in a virtual image if your object is closer than the focal length to the center of the lens. I'm not going to go through all the derivation, but if you're interested, you can take a look in the book. But the basic idea is what we're using here is something called the thin lens approximation. Which says that it turns out that in this situation you have your converging lens, for example, the center axis. And let's say you have a light ray that's parallel to that center axis, some distance y, coming in a perpendicular distance y above the axis. And again, that's going to be bent. If it's parallel, it's going to be hit here, and that distance is the focal length. Well, if I look at this angle theta, let's call this angle theta, then we can just do the trigonometry and say that the tangent of that angle is that perpendicular distance y over the focal length, little f. But for thin lenses, what we're typically dealing with are situations where the angles are small. Okay, so this is kind of an exaggerated picture. What we're usually dealing with is something like this light ray comes in, and then this light ray is bent to something like that. And we have a small angle here. And you might know that if you're using, I draw this, so this is f now, this is y. Well, here's some distance, the hypotenuse of this triangle. This is a right triangle. This hypotenuse is some distance r. If this angle is small, then y over r is approximately equal to y over f. And y over r is the definition of the angle theta in radians. Okay, if you measure theta in radians, by definition, it's this distance divided by the radius. So we can say that this is approximately just equal to the angle in radians. And then you have to go through some geometric arguments, which I'm not going to go into. But what happens is you find that any light ray is always going to be bent at the same angle. Okay, so if this is angle theta, but a light ray coming in from here, as long as it enters the same, or as long as it's the same distance y above the center axis, will be bent at the same angle. Okay, so that angle from, how do I want to draw this? The angle of deflection away from this original direction is the same angle. You can go through some trig and some geometry, and what it turns out is that based on that fact, based on the fact that the angle is equal to the perpendicular distance y divided by the focal length, you can work out what's called the thin lens formula. Which is 1 over the focal length is equal to 1 over d1 plus 1 over d2. Now, what's that mean? Well, f is the focal length. D1 is the distance from the center of the lens to the object, or to the source. Say the source or the object. And D2 is the distance from the center of the lens to the image. Okay. So if we apply this to, let's just try a quick example just to show you how this works. But if you have a focal length of, say, 12 centimeters, okay, and you have an object, so here's your focal length, f, and this is 12 centimeters, and you have an object that is a d1 of distance of, say, 18 centimeters away. Calculate, use this formula, plug it in, what do you get for d2? So you have focal length of 12 centimeters, d1 is 18 centimeters. What do you get for d2? Where's the image going to form on the other side of the lens? (36 centimeters? Okay, so you have 1 over the focal length minus 1 over d2 gives you, or excuse me, 1 over d1 gives you 1 over d2. And so you have 1 over, I'll just keep it all in centimeters, 1 over 12 minus 1 over 18 is 1 over d2. And then you say d2 is 1 over all of that. And that gives you 36 centimeters. Okay. So somewhere 36 centimeters away, you're going to get a real image form that's inverted on this side of the lens. Okay. What if, same focal length, what if d1 is equal to 6 centimeters? So now the distance away to the object, from the object to the lens rather, is less than the focal length. So here's the object, here's the focal length. What are you going to get for D2? Work it out. Well, it should be pretty easy, right? What are you going to get? 1 over D2 is going to be equal to what? Not negative 1/6, negative 1/12, right? Negative 1/12. So D2 is going to be equal to negative 12 centimeters. What's the negative mean? Not reflection, but what did we just talk about? If it's inside the focal length, you get not a real image, but a virtual image. So the negative here in this case means a virtual image. You're going to get an image that is apparently formed on the same side of the lens as the actual source, and that's where the negative sign comes in. So you have to be able to interpret the signs correctly. The same formula actually applies for diverging lenses. We won't go into the details here, but basically this is the formula about which most optics is built around. Okay, now if you get into sophisticated applications, you have to deal with non-thin approximations. You have to deal with things like chromatic aberration, where different colors might be refracted at different ways. But when you're constructing just basic optical equipment, this is sort of the formula that governs it all. Okay. If you need more details, you can certainly go and take a look in the book.